Welcome to your online training module, Introduction to Medical Entomology. In this unit, we will focus on measuring technical failure in vector control and surveillance systems of major vector groups responsible for transmitting diseases in the region. When surveillance tools fails, it can lead to wasted resources, efforts, and continued disease transmission within the region. In this unit, we will recognize, measure, and troubleshoot these major issues. Now, let's take a look at Vectorlandia. After months of surveillance efforts, they are now facing new challenges in their surveillance efforts.
Over the past month, the Vector Control Unit has supplied labs with mosquito samples for identification and analysis, but control measures like spraying and larviciding haven't significantly reduced populations. The labs suspect possible insecticide resistance and plan for future testing. Some traps also stopped capturing mosquitoes despite earlier high counts, prompting the team consider a formal maintenance protocol to troubleshoot surveillance tools.
Let's start with insecticide resistance. Resistance is a heritable trait, meaning certain individuals in a population can survive exposure to insecticides that would normally be lethal. Over time, these survivors reproduce, passing along resistance genes. The result? Insecticides lose effectiveness, requiring higher doses or new compounds. This is one of the biggest technical failures we face in vector control. One of the most common mechanisms is metabolic resistance. Insects develop biochemical systems that detoxify or break down insecticides more efficiently. They produce larger amounts of detoxifying enzymes, or more effective versions of them. This is like giving the mosquito a stronger liver. It neutralizes the chemical before it reaches its target. Another major mechanism is target site resistance. This occurs when a genetic mutation alters the protein that an insecticide normally binds to. For example, knockdown resistance involves changes to sodium channels, while altered acetylcholinesterase can make organophosphates ineffective. Or modified GABA receptors can block certain insecticides. In each case, the insecticide still enters the body, but it can't bind effectively, meaning no toxic effect. Another resistance mechanism is cuticular resistance, which is more physical. Here, the insect's exoskeleton changes, becoming thicker or chemically altered. This slows down absorption of insecticides, giving the insect's metabolism more time to detoxify the compound. It's like wearing armor. The insecticide simply takes longer to penetrate. Finally, we have behavioral resistance. This occurs when insects change their habits to avoid exposure. For example, insects might avoid sprayed surfaces, develop bait aversion, or even change resting patterns, as the case with some mosquitoes that now prefer to rest outdoors instead of indoors, which undermines indoor residual spraying against malaria. The causes of resistance come down to natural selection under pressure. When we use the same insecticide repeatedly, resistant individuals survive and pass on their genes. Factors that drive resistance include genetic mutations, intensive and repeated use of one insecticide class, and the misuse of insecticide, such as applying incorrect doses or poor timing. This is why resistance management is critical to sustaining vector control programs. To monitor resistance as part of a vector surveillance strategy, researchers would need to monitor possible resistance using traditional bioassays, as well as modern biochemical and molecular techniques. To manage resistance, we must monitor it effectively utilizing approved methodologies, such as bioassay testing. These tests expose field-collected insects to insecticides and comparing mortality to a susceptible strain. In the laboratory, tests such as diagnostic dose bioassays measure presence or absence of resistance, and dose-response bioassays quantify resistance levels. Other tests include biochemical assays, where researchers test enzyme activity, providing insight into metabolic resistance. Molecular assays, using technology such as PCR, to detect mutations and knock down resistance at the genetic level. And field efficacy monitoring, testing insecticides under real-world conditions using sentinel cage trials test. Together, these methods give a complete picture of any potential resistance. An integrated strategy starts with phenotypic bioassays. If resistance is confirmed, we add biochemical or molecular assays to pinpoint the mechanism. Then, based on the findings, we adjust management, rotating insecticides, combining interventions, or switching chemical classes. This cycle of monitoring and adaptation is the backbone of resistance management. Beyond resistance, surveillance tools itself can fail. Failures may occur at the trap level, program level, or due to ecological and social factors. A faulty trap doesn't just give poor data. It may mislead us into thinking vector densities are lower than they are, causing underestimation of risk. Likewise, poor program management can leave whole areas unsupervised. Trap failures may be due to mechanical or power failures, poor maintenance of traps, inefficient trap design, use of wrong bait or lure, or even incorrect placement of trap, for example, having traps in direct sunlight when shade is required. Even vandalism or damage by animals can compromise performance. Each of these issues can lead to inaccurate data. Surveillance programs can also fail because of systemic issues caused by lack of surveillance standardization, inadequate resources, poor data management, and insufficient follow-up. These reflect broader programmatic weaknesses rather than just trap-specific problems. Sometimes failure stems from biology itself. For example, low vector density may result in traps collecting low numbers, even if they work perfectly. There could also be insecticide resistance, which may reduce catches in baited traps. And lastly, insect behavioral changes may reduce trap attractiveness. So, low catches are not always a technical failure, but they may reflect ecological realities and must be monitored. Finally, external and social factors also play a role. In some cases, communities may reject surveillance programs, which leads to traps being tampered with. Environmental conditions, such as weather, disrupt trap function and deployment. Lastly, political and social instability may disrupt ongoing surveillance operations. These challenges remind us that surveillance is as much about people as it is about technology. So how do we recognize equipment failure? The most obvious sign is no or very low insect catches compared to the researchers' expected levels. But low catch can also mean low vector density, so we must rule out ecological causes before blaming the trap. However, some indicators that traps are not functioning include dirty or clogged trap components, physical damage like torn nets or broken wires, weak suction or lights not turning on, or even battery or power failures. Effective management of equipment failure requires a proactive and systematic approach. Personnel should be trained in basic troubleshooting procedures to enable rapid identification and resolution of technical issues. Regular maintenance schedules must be followed to reduce the likelihood of unexpected malfunctions, and all failures should be documented in equipment logs to support monitoring and accountability. In addition, clear timelines for repair or replacement should be established to minimize operational disruptions. Implementing these measures ensures that surveillance equipment remains reliable and that the data collected are accurate and scientifically valid.